All
Hello.
those lovely Zoom bombing.
Hey, Guido.
How's it going?
It's going all right. People are just rolling in, so perfect timing.
Sweet, sweet.
And
Right, we've got the gallery view on the live stream. Perfect.
Oh, nice.
So everyone who's joining the Zoom just now, we are live streaming. We'll have a few words of intros, but just note that you're going to be recorded as well as on the broader internet. Rolling in, so perfect timing. That was an echo loop. So make sure you be conscious of what you say or what you display in the meantime. Hopefully, we'll have a lot of fun in the process. I think, Guido, is Matt joining later?
They should be, both Luigi and Matt should be joining any minute. Yeah.
Perfect. So we don't need to wait for them because they're in the second half. And I think I'll kick things off in just a minute here.
I keep having to admit Brett Morgan because I think Brett cannot join for some reason.
Oh no,
so
Brett!
If you're out there, I'm sorry.
I know Brett. I wish I could let him. Anyway, let's get the meetup started. That sounds perfect timing. So, hi everyone on live stream, on YouTube Live, as well as in future recordings. Thanks for joining us for another WebAssembly SF. This is our second live stream event. We're trying things yet different once again, and I'll go through all the details shortly. But before we get too far into it, we have a code of conduct. And if you haven't read our code of conduct, it's on our Meetup page. And to summarize, it's basically be excellent, be awesome. If you're in the live stream, if you're on the Zoom, in particular, pay attention to what you say or what you do. We don't have any tolerance for inappropriate behavior. And respect for everyone is always a good thing. This meetup is our fall event. We have two awesome talks lined up for you. They'll go into the details, but it's all made possible by the help of our friends at Solo.io, Betty, who's the co-host, and Yuval and his team will be speaking later. They provided the Zoom live streaming infrastructure. So thank you, Solo. Quick virtual applause, and thank you. Yeah, I don't want to belabor the point anymore. I'll be on the Zoom chat for those in the Zoom. If you have any questions for the speakers, as well as anyone on YouTube, there's also the YouTube chat should be live. Feel free to answer questions. We'll have time at the end for questions. And between the sessions, and I guess after the sessions, we'll also be leveraging Zoom's breakout room features. So those who are live can meet other people and chat a little bit. So yeah. I think that's all I have to say, and now I want to hand it over to the Solo team.
All right, welcome everyone. Let me share my screen. Here we go. You hopefully are seeing some slides now. Yes. All right. So. Welcome everybody, I'm Yuval, I'm the Chief Architect at Solo.io, and with me Shane O'Donnell, he's also from Solo.io naturally, social engineer, and we would like to talk to you today about a developer experience that is Docker-like for extending Envoy and other cloud-native products using WebAssembly and WebAssemblyHub. As the first step, we'll do a quick introduction to Envoy, so we all kind of have a baseline and we all talking about the same thing, so that way you don't need any prior knowledge. It's going to be very high level. I'm going to talk a little bit about Envoy, the control plane, the data plane, where WebAssembly fits in, then how do we enhance the developer experience. And then finally, we'll have a short demo where we show live, hopefully, a filter that was written in Wasm and used by Envoy. And in the end, we'll have some time for questions. All right, so let's continue. First, what is this product Envoy that we're talking about? So in the cloud native ecosystem, it's a very popular product right now. It's a cloud native HTTP TCP proxy that is used to implement various products on top of them. One of these products is our API Gateway Glue. So you can use Envoy to be your data path layer and create an API gateway on top of that. Other products are service meshes, most notable Istio. And there's a lot of stuff you can use Envoy for. So essentially it can be used as front proxy, a middle proxy, or a sidecar proxy. And part of the appealing feature set that makes Envoy used in so many different use cases is the ability to extend it. Now, today Envoy is written in C++, and in order to extend it, you essentially need to write C++ code and rebuild Envoy with your filter code or your extension code compiled into Envoy. And that's what we do in Sol.io. We have our own distribution of Envoy with Glue that we use to provide extra value on top of the core Envoy. Now, Envoy is 100% open source. There's no company that sells it's not like the Nginx where you have the core and the plus. Envoy itself is 100% open source, and we extend it with using these extension points. And we'll get to those extension points in a few minutes. All right, and this is just to illustrate that Envoy itself is a complicated piece of machinery, and in order to interact with it, you do need some help usually, because it has so many features and been extended by a lot of companies to cover very different use cases. It's a very, it's a tool with a lot of configuration and customization options. So what we've done in Solo is create a product on top of it. We call it Glue, that allows you to abstract some of the complexity that Envoy has, provides simpler use cases, and essentially give you a specialized API for that use case. So Glue specifically is an API gateway, and the way it works, if you can see this diagram here, Envoy essentially connects to Glue to get its configuration, but all the data goes only through Envoy, only through this proxy, and during the data path, there's no really communication for Glue as for configuration. So Glue asynchronously delivers the routing information, you know, this request should go here, this request should go there, in a way that's a simpler abstraction by using Kubernetes CRDs in Glue's case, and converts it to Envoy more complicated or more complex configuration format. Now, to illustrate how the request flow goes today, and the reason we're doing all this intro explanation is just to explain where the Wasm fits in later on. So the way requests work today, let's first start with a configuration path or the control path. Essentially, Glue is what we call a control plane for Envoy, and Envoy is what is called the data plane, right? So the data plane is the path user data requests go through, and the control plane is the out-of-band configuration plane where you deliver configuration to the data plane. So in Glue case, a user configures what we call a virtual service that has a route that in this case says everything goes to service 1. And we also want to apply an open policy agent policy, right? So this is that configuration on the bottom right. Glue translates that configuration to Envoy configuration and delivers it to Envoy. And Envoy asynchronously, in an eventual consistent manner, applies this new Glue configuration. Now, as far as the data path, at this point, the configuration is already propagated to Envoy, and a request comes in. In our case, it's a post request. the request goes through a series of filters that can manipulate the request, right? So in this example, we have here a set of 4 filters: external auth, rate limit, a gRPC transcoder, and a router filter. And the request goes through each of them in order to be processed by Envoy. So the first filter, external auth, calls out to an external authorization server and asks if the request is authorized. And if it authorized, it continues to the next filter. And the next filter checks if we need to apply rate limiting, return 429. If everything is okay with rate limiting, then it moves on. The last filter in this example is a gRPC transcoder that turns a REST request into a gRPC request, because a lot of time on the backend, especially when you're using languages like Go, the backend will be a gRPC service. And this allows you to still give a REST interface that is easy to consume, but still have the backend as gRPC. So this filter here in the chain transforms the request to a gRPC request, and then sends it to the router filter, and the router filter sends it upstream to the destination. Now, this is a very powerful mechanism, and we can also extend this extensions using C++ code that gets compiled into Envoy. And let's talk a little bit, how do we extend the data plane? So the way we do it with Glue, we write custom filters, right? So Envoy build system is engineered so you can very easily bring in upstream Envoy and add your code on top of it, right? Add some extra code, rebuild the binary into a new Envoy binary that now includes your extension. Now, the advantage of this is very fast to run when it runs, but you need to rebuild Envoy, which is requires a bit of effort. Every time you make a change, you have to rebuild all of Envoy, including Envoy core, all of Envoy built-in extensions of filters. You need to understand asynchronous C++, and that's pretty much the only language you can use. There's a little bit talk about starting to introduce Rust to be used for native filters, but it's not there yet. But the advantage is it's very fast, and the code is strongly typed, so it's safe to write. Let's continue. Ideally, what we want is something that gives us all the other check marks, and that's where we're talking about WebAssembly. And I'll hand it off to Shane to tell us a little bit more about that.
Sure, thanks, Yuval. So, now that we're all Envoy experts, we can kind of sit here and think, how can we solve some of these problems using WebAssembly? So if we go to the next slide, WebAssembly is kind of a little bit of a misnomer because it's not really dedicated to the web or necessarily assembly. So even though it was originally built with the web in mind, it was actually designed in such a way that it could be embedded in other environments. So, Google came along and saw this and realized this would actually have some pretty cool synergies with Envoy, especially when it comes down to filters. So when we think of WebAssembly and all the benefits it can give us, we got to think about what kind of features and characteristics of WebAssembly would we like to see that we could maybe take advantage of in Envoy. So on the next slide, the first one is that it's portable. So, I don't have to target any specific platform. I'm just targeting the WebAssembly output format. And then, whatever runtime on whatever environment we're running on, we'll make sure that it's optimized to run in that environment. So it's one more thing I just don't have to worry about. Next up, it's secure. Considering that, Wasm obviously has its origins in the web, it's kind of designed to be run in a browser. And, a browser is kind of implicitly or explicitly a hostile environment. You need your Wasm applications not to be able to do nefarious things and attack each other. So, by design, it's run in a sandbox. And in order to break out of that sandbox, well, it can't break out of that sandbox. So it's inherently just very secure. In order to communicate with the outside world, we basically have to use a specific set of predefined APIs, and you can tweak permissions with those and say this application can't talk to the network or whatever you need to do to lock it down. But the main point is that it's pretty secure, which is something we really value, especially if you think about something that's going to live on the edge of your Kubernetes cluster as a proxy. That's awesome. The next thing that we really like about it is that it's fast. And as you can see in this slide, WebAssembly is usually compared to JavaScript, and it's kind of a solution for people who say, oh, I want to run a bunch of WebGL, or I want to run some really complex algorithms and some really process heavy number crunching code, and JavaScript just isn't up to it. And while WebAssembly is going to be faster than JavaScript at that, what's actually surprising to a lot of people is that it's almost as fast as native C++. So if you write some C++ code and you compile it to a native binary, and then you write some C++ code and compile it to WebAssembly, obviously it's a little bit slower, but right now we're seeing maybe 10 to 20% performance degradation, and that comes along with this is still pretty early stages, so we're pretty optimistic it's going to get even faster. But when you consider all of the advantages that we get from running WebAssembly over like you've all said, being a native C++ developer, you don't need to know as many things in order to be productive in WebAssembly. So that performance gain really isn't that big of an issue in most arenas. So that brings us nicely into the next thing, which is you can kind of write this in any language. Right now we're kind of supporting C++, Rust, AssemblyScript, and TinyGo, but theoretically you could write any language, basically any compiler tool chain that can output like the bytecode format that's the intermediate representation, can write a WebAssembly module that could theoretically be loaded into Envoy, which is awesome. Like, I wouldn't recommend it, but you could probably write something in COBOL that you could theoretically run in Envoy, which is awesome. And then finally is WASI, which is the WebAssembly system interface. And this is kind of a core tool set that solves the problem for what do we need to do to be able to run these WebAssembly applications as if they were system programs. And we don't use a huge surface area of the API here in Envoy, but it's just something that brings more people into the ecosystem, gets more eyeballs on WebAssembly, and just brings the whole ecosystem as a whole up, which is awesome. So that checks pretty much all the boxes that was on one of the slides we looked at previously. We can use any language. It's fast. It's safe. You don't need to recompile Envoy, which we really can't overstate. That's a big deal, because unless you want to maintain a distribution of Envoy and become a C++ developer, or even more than that, an Envoy developer, you probably don't want to get into the low-level Envoy API if you're just trying to write a couple of web filters, which is awesome. And it's easy to use. It's in a language you're familiar with, and there's not a huge surface area for you to touch. Which brings us to how do we harness this specifically in Envoy? So if we go back to the diagram that next slide, sorry. This is the diagram that Yuval was showing earlier, where we've built these custom filters, we've baked them into Envoy and C++. And what some very smart guys at Google have come along and said is, what if we build WebAssembly support directly into Envoy? And that's pretty much what they've done. So next slide, they've got built in this Wasm support natively. And what they've done is they've embedded the V8 runtime, and they've exposed a way to load these WebAssembly modules, which are going to act as Envoy filters via the control plane in Envoy, which means that not only do you not need to maintain your own distro and fork of Envoy and maintain all kinds of stuff that has to do with that, you don't even need to restart Envoy in order to deploy these. These can be live deployed at runtime, zero downtime for your users, and you could pretty much hot swap these as you go, which is really, really powerful, and keeps in line with a lot of the core principles of Envoy, which let you do things like this. So how this works is that Envoy exposes a ABI under the hood. And this is an application binary interface, which is a pretty low-level system. So you can see here there's an example call with some parameters. And you can kind of get a feel for this is going to be pretty powerful. And you can use it to create any filter that you could create with a native Envoy. Almost any filter, at least, you can create using this low-level interface. But it's still kind of tricky to use. So for that reason, people have actually started building SDKs on top of that. Right now, we've got support for C++, Rust, AssemblyScript, and TinyGo. But like I said earlier, technically it could be anything. And the great thing about these SDKs is that they're higher level. There's something that you could pretty much jump into and use right away. And you can use them in whatever your language of choice is, which is great. So now that we've got people writing code in their own languages, building these filters for Envoy, and pretty much shipping them in the application, you can go forward. Next slide. Next slide again. Yeah, so we've pretty much harnessed the use any language, the fast and the safe and the easy, the need to compile, but we haven't really touched easy yet, because going from 0 to I've written my own custom filter that uses this SDK, that uses this API that deploys to Envoy still is kind of hand waving away a couple of steps. So in order to make that a little bit easier, we decided we'd kind of take a wholesome look at the overall developer experience. And, on the next slide, just before we jump into specifically what we did at the developer experience, we saw this tweet and we just thought this was, really something that we believe as well, that this guy's saying that WebAssembly on the server could be the future of computing. And that's like a really strong statement, but, we don't really believe that that's overstating it, because, if this was built 10 years ago, we could use this instead of Docker, which is pretty powerful. So, in light of that, and given that this is the future, how do we get more people onto this? How do we get the future here closer? And how do we lower the barriers to entry to using this? So what we've come up with is WebAssemblyHub, which is kind of an overall idea of how do we make this easier, more approachable, and how do we address the primary pain points for developers? So we've identified 4 main things, and these are them here that are kind of the first barriers you hit if you want to do all the stuff we've been talking about. First of all, how do you build it? How do you go from an empty IDE to having a fully runnable Wasm module that you can deploy into Envoy? So in order to do that, we've taken some inspiration from some tools that people like in the community. So we kind of have something that's quite like if you've ever used Create React App or ng-new, if you're a front end person, just a one-line script that'll fire up a whole IDE, which pretty much are a whole folder that gives you a dev environment, a tool chain. You'll get scaffolding and boilerplate code, pretty much like a Hello World app, and you're just ready to run with it right off the bat. You don't have to worry about like setting up things like Bazel, or you've already got your package JSON with all your dependencies. It's all set for you. You can just focus on writing your own filter code, which is really what you want to focus on. The next step is, so you've used our build tool, you've got our environment set up, you've built this and you've got a filter.wasm, but how do you get it from your computer onto the server? So in order to do this, we've taken some inspiration from Docker and wrapped it in an OCI image. So we're using the same technology that Docker images use to wrap up your filters, and then we're pushing them up into an image repository, which is what WasmHub, the website is. And you can also use this to discover images that other people have used, similar to Docker Hub. So if, say, you're trying to like pull something out of a JWT token, or any kind of common use case that you might see in these filters, you can see if someone else has built it and save yourself the trouble and just reuse things that the community has put out there. And we're seeing a bit of that already, which is really cool to see. And then finally, deployment is something, again, that we really admire what Docker has done here. Where once you've got Docker set up, you just do Docker run image name, and then you've got whatever that is running. And that's something that we've tried pretty hard to emulate, and you'll see in the demo coming up. So next slide, you can see that we've pretty much checked the easy box, or at least we hope we did. This is all open for community feedback. We'd love to hear you guys' opinions on how to make this even easier if possible, or some things that you guys are struggling with. And then after that, I'll pass it back to Yuval.
Yes, and currently we target Envoy, but this can also be applied to other products. For example, Open Policy Agent has WebAssembly support as a work in progress. There's KRaslet that allows you to run Wasm binaries in Kubernetes. And they all share the same problems of you need to build, deploy, distribution, discovery. So hopefully in time, our tooling will extend to these other projects as well as other developer use cases like testing, unit testing, debugging, that sort of things. Without further ado, let me just change the share here. Share screen. Yeah, 1 sec, the Zoom is misbehaving. All right, so here we go. I hope everybody's seeing my VS Code now.
Yep.
I will just do a brief demo with how Wasm looks using assembly script and Envoy. And the Envoy WebAssembly script runtime. First thing, 1 sec, let me move my face here. All right. first thing I wanted you to guys note is the Envoy configuration. And this is a very, very basic getting started demo, right? So when we use Wasm, we also abstract some of that, and we'll get to that later. So the first step is to define the Envoy filters, and then there you define where your Wasm module is. In our case, it's in build optimize.wasm, and various stuff like configuration. And we also have the router filter. That's the same router filter we saw in the slides. So you essentially define a WebAssembly filter and tell it to load a WebAssembly file. Looking at the TypeScript code, or rather assembly script code with a TypeScript suffix, so we get code highlighting. We see that filter code itself, and you can see all these callbacks that were previously low-level C-like functions are now TypeScript functions, right? So this function gets called when request headers arrive. So for every request, we get a call to this callback, and we can decide what to do. In this example, we perform an HTTP call out, which you can see right here, an HTTP call, and the result of this call is returned to the callback right here, that based on the result decides whether or not to allow or deny the request, right? So we make a call out to an external authorization server. If it returns 200, we allow the request, and if it does not, we deny the request. In addition, also just for demo purposes, we also implement the response header, and we also add a header. I can even change it here so it'll be a little bit different than before. Now, to make this work, I'll just build it really quickly. Here we go. And then I will run Envoy, and you can see here the Envoy logs. Let's clear the terminal. On the other terminal, if we do a curl, we get the forbidden. But if we do a curl to a path that is allowed by the authorization server, you see that we get an authorized response. In our case, it's Postman echo, so I just get the request back as JSON. In both cases, you can see that the response header was added, and we have a low Wasm appearing in the response, and the log from the Wasm filter appearing in the Envoy logs. Right, and if there's any questions, feel free to ask. In the meantime, let me see here. I'm gonna change the share. I also want to note WebAssemblyHub, where you can explore and discover various images, various projects, download them. It's a very Docker-like experience. You know, it gives you the command you need to use. In our case, Wasm pull. It's very similar to Docker pull. And this is the GitHub page for Wasm. If you'll go to the releases, you can download Wasm itself. And if you go to WebAssemblyHub docs, you'll find plenty of examples, tutorials, all the good stuff. And obviously, we love our community. So if you have any questions, you can file an issue, open a pull request, even better, and be engaged. There's a Wasm channel in the solo Slack if you have any questions. So feel free to hit us up. And that's my demo for today. If there's any questions, we left intentionally some time for Q&A, so please feel free if there's any questions.
Excellent. Well, people in the Zoom, feel free to unmute yourself, your camera, to ask your questions. I already see Sam is geared up. And for everyone else who's not asking a question, just stay on mute, but queue up as needed. And I'll be monitoring the Zoom as well as the YouTube chat.
Yeah, I was curious about the name WebAssemblyHub. Sounds very generic. Is there plans to make it like a generic software center for WebAssembly software? Like, or I mean, as opposed to
So our goal, we also defined. Maybe I'll share the screen again. We're in the process of defining a spec and getting it more formally recognized. So if you, one sec, let me share my screen. we're trying to use the OCI artifact specification to define a standard way to push Wasm images to standard OCI registries, you know, like a GCR, Harbor, Azure Container Registry. All of these registries can contain today Docker images, but they're not limited to Docker. They can contain other OCI images. And we started with Envoy because we know Envoy very well, but we also hope to extend it to other artifact types. For example, open policy agent policies can also be compiled to WebAssembly. And hopefully in the future, Wasm programs that can be run in K-Rustlet, you know, and essentially bring this Docker experience to other Wasm use cases. I hope that answers the question.
Yeah, and if to Yuval's point, if you're working with kind of like different, you know, targets effectively, we'd love to have you check out the spec, because one of the things we're trying to do with the community is like what kind of metadata and stuff need to be stored so that it can apply, so that we're making sure it applies to a broad range of targets.
Yeah, so an example of some of the metadata that we were already using for the Envoy filter stuff is in the particularly like very start of Envoy, the ABI itself was, for at least for the filters, was very unstable. So it would change pretty frequently. So we use the metadata to keep track of which versions were going to be supported. So if you go to WasmHub today, that's also like baked in there to say, hey, this was built and it'll run on Istio 1.3 and Glue 1.5. But if they make breaking changes, then you might have to recompile it and target different versions.
There's a question in here from Tim saying, I'm interested in the storage persistence aspect. Is the Wasm execution stateless, or can it hold data over a series of function calls?
Are you talking within Envoy? So filters generally within Envoy are kind of discouraged from keeping state. They can keep state, but you got to be very specific on the way you do it. Usually, if you want to get more data inside Envoy, you create a stat, a metric, kind of Prometheus metric, like a counter or a gauge. If you the problem that with filter holding state, that obviously will increase Envoy's memory consumption, and it increases the complexity because of the way Envoy works. They try to isolate each worker thread to be completely independent from the other threads to maximize performance. So yes, you can hold some sort of a global state, but you gotta kind of think about it to make sure you don't impact performance too much.
Yeah, it's worth calling out in the context of Wasm more broadly, and in particular with WASI, that there's a lot of effort to define, state and storage as a first-class citizen. So some of the folks here work on WASI, and there is discussions around how to expose it through a WASI interface, and maybe outside the context of an Envoy filter, but in other cloud and non-web use cases for sure.
Yeah, that makes a lot of sense. So as far as Envoy doesn't support a lot of WASI APIs, specifically because Envoy needs to retain control of I/O. Because Envoy has its own I/O loop, async loop, it's gonna make sure all the I/O goes through that loop. Otherwise, a single I/O function can block the whole Envoy thread. So Envoy does use some functions of WASI that make sense, get the time, stuff like that. As far as WebAssemblyHub, it's obviously, it doesn't really care that much what the module is doing, so it shouldn't be a problem.
Tim's got a follow-up question. Can this also be called over HTTP as opposed to command line?
Are you referring to Wasm itself? So, sort of. We'll say yes and no. So Wasm itself is a command line tool very similar to Docker, but eventually Envoy gets its configuration from the control plane, right? In our example, we showed Glue, and Glue can be configured using Kubernetes CRDs. So in a roundabout way, yes, because when you interact with Envoy, you'll probably do it through a control plane, and the control plane will probably have an API.
I see, Thomas, you turned your camera. Do you have a question? Or just showing your answer background?
Yeah, and I typed slowly enough. It's maybe better doing it this way. Just wondering about overhead crossing the, I mean, you know, generic Wasm question, but the overhead of crossing the boundary into the Wasm machine and coming back out again, sort of, do you have to make sure when you're designing the packet processing ABI that you don't get too fine-grained, or is there a point where you say, you know, maybe I ought to write this filter in C++ after all, just so I'm not doing that? Or
yeah, that's a very good question. So the ABI is optimized to give you the minimum amount of data you need. So for example, process the callback for the headers doesn't give you the headers, right? Because then you'll have to copy all the memory into the Wasm sandbox. Instead, it gives you the header size and allows you to call a different function to get the headers if you want. So you only pay the cost of copying if you really have to. And it also allows you to request a specific header, again, just so you don't have to copy all the data. So yes, Wasm is sandbox. Every time you manipulate memory, it has to be copied into the sandbox. And if you want the modification to be applied to the request, it has to be copied out of the sandbox. But the API was designed in such a way that it doesn't happen by default. And rather, when you write the filter, you are very aware on the time you pay that cost. Another thing that can impact performance is the type of VM you use. There's V8 and Wasm supported, right? So V8 might give you faster loading times, but slower run times compared to Wasm. So yes, it is a problem that's mainly been addressed in the way the ABI was designed. Still, you know, if you're doing large body manipulations, a C++ filter will probably be faster because of that copy back and forth that would need to happen to facilitate that, right? But for example, if you want to create a stat that just creates a stat on the sizes of the body, you can get that very cheaply, right? Or if you want to manipulate a single header, you can do it pretty cheaply. Yeah, but the API gives you the control, so you only pay the cost when you have to.
Thank you. Yeah, I'm just going on intuition, and we know how unreliable that is. I would have guessed you might be more concerned about trying to minimize the number of method calls, and the data copying might be less of a concern, but. I'm sure you guys have, well, you've actually done this. I'm just guessing about it. So you've probably thought it through a bunch more, and even have sort of probably have the numbers to show that, yeah, sort of minimizing data copying is the right thing to do.
And there's actually been previous talks at Wasm SF, which is on our YouTube channel, about the data copying overhead, in particular for WebAssembly. And how the WebAssembly, the different groups within WebAssembly, both at the overall specification level as well as WASI, are focusing on reducing that overhead, as it is a particular area of concern. So I can refer to that later.
All right, thank you both.
Yuval, there's another question here. Is how is the TinyGo support? And then they saw that someone had recently added TinyGo WASI support. And are y'all using WASI TinyGo, and how is the performance and module size?
So we're using specifically TinyGo that is built for the Envoy ABI and not the WASI kind. As for the binary size, Shay, maybe you know better than me. I'll have to.
Off the top of my head, I have to double check it, but it's in terms of like support from the Wasm side, it's got the exact same support as AssemblyScript and C++. If you do like a Wasm init, TinyGo now shows up as an option, and it'll show you which versions of all the various Envoy distros that support the version that TinyGo is targeting. And the TinyGo support that was contributed to Wasm itself was actually contributed by one of the creators of TinyGo. So I haven't used it too much myself yet. It's definitely high on my to-do list, but given that it's coming from the author himself, I'm pretty sure the support's probably pretty solid.
And then Thomas has a question on hearing a little bit more about the OCI spec. What kinds of applications are able to consume OCI images, and what benefits does Wasm bring to those applications?
Well, a big one is Kubernetes, naturally. Another one is Helm. Helm charts for Kubernetes can be stored in OCI. If you look at the OCI spec, there's another company that allows you to release their artifacts also as OCI. Essentially, the problem OCI solves is the distribution, right? You have a binary blob and you want to get it somewhere, right? So from the developer laptop into your cluster in the cloud. So that's kind of a standard way to package it and send it away. Now, Wasm itself, it's not exactly beneficial to OCI per se, but rather when you use Wasm in the context of cloud application, you have very similar problems of distribution that you had that Docker solved, right? And we can use the Docker solution, OCI images, to solve the same problem, right? So if we have, 1,000 envoys running in our cluster and they all need to get this updated copy of the Wasm filter, we can use OCI to distribute the Wasm image from the developer laptop into a registry and from the registry into the cluster.
Cool. Any other questions? Let's see.
I asked the TinyGo question. I just wanted to say thank you.
Thank you.
Yeah.
Any thoughts on dependency management akin to NPM?
So that really depends on the language. Usually you re-leverage whatever dependency management the language already has. So with Rust, it'll be Cargo. With AssemblyScript, it'll be NPM. But that's not something Envoy ABI deals with. But rather, when you write an SDK for a new language, for example, we wrote the AssemblyScript one, then we decided to re-leverage the existing NPM ecosystem for distribution. So that's usually a decision you make when you create a new language SDK.
Cool. Any more questions? Because if not, we can do a little breakout room. What do you think?
So one thing, y'all wrote the AssemblyScript SDK, I may ask?
Sorry, what was that?
Y'all wrote the AssemblyScript SDK for your, awesome. Yeah, I'm on the AssemblyScript team. If you guys have any feedback on AssemblyScript or ever want to talk, we have like weekly meetings and stuff, or bi-weekly. So yeah, feel free.
Nice.
Or open issues, we'd be happy to look at them if you find any. Not saying there will be some, but just saying if you find
Awesome.
Yeah, we had initially before inheritance was properly supported, but now it's working great.
Cool, awesome. Yeah, thank you.
No, thank you.
I think that's good. A good place to pause. I'm not sure what's gonna happen in the live stream once we go to the breakout room. We'll figure it out all together. But in the meantime, if you're watching a live stream, there's probably a little bit of a pause before we get to the next speaker. And yeah, for everyone who's in the Zoom, Betty has helped set up a bunch of breakout rooms. You want to explain how it works?
Yeah, so I'm just gonna, we're gonna create like probably 5 rooms so that we have like, 5-ish people per room, and it's gonna be random. So it's gonna be, we'll see what happens. All right, so we'll be in, we'll have folks in there for about 15 minutes, and then we'll transition to the next speaker. All right, ready, set, go.
All right. People are popping back in. I think the live stream is just catching up now. Awesome. Awesome. Well, that was cool. That worked. And anyone who's watching the live stream, we're back. So feel free to get back into the video. And oh, we got some new faces showing up as they're getting back from their breakout rooms. I think I'll give folks a few more minutes to come in. All right. Sounds good. Well, I think we're ready for our next talk from the folks at Rive. I'm not going to spend too much time describing it, but I've been following their progress for a while and keep on seeing WebAssembly updates. So I'm super excited to hear how they use it. I think you'll enjoy it. So with that, I'll just hand over. Luigi, are you going to kick things off, or is someone else in your team going to?
I think Matt's going to start us off, but I'll be in there.
Perfect. All right. Take it away, Matt.
Thank you very much. Now let me work out if I know how I can share. How's that? Can anyone see my slides? Perfect. Well, thank you for inviting us to chat to you for the next half hour, 40 minutes. We are Rive. We are a company that has created an animations platform that can create animations across or can run animations across multiple platforms. My name is Matt Sullivan. I am a software engineer on the Rive team. And I'll introduce Luigi, who is muted, is our
Sorry.
There you go. I'm like staring at you going, is he going to do this?
Hey, I'm Luigi. I work with Matt. I'm the chief tech at Rive. Basically, just write a bunch of code.
And so what I want to do tonight is to talk about our use of WebAssembly. We use a lot of different technologies at Rive. We use Flutter, we use Objective-C, we have some Kotlin in there as well, C++, JavaScript. And our engineering team is 4 people, so you've got half of us here tonight. And we're going to tell you a little bit about how we're using WebAssembly and how we're using it to basically make it that size of a team as effective as we can be to be able to deliver different runtimes across different platforms for displaying our animations. One thing to notice is that we have been using WebAssembly for about 2 months in earnest, so we are relatively new to the platform. But first and foremost, what is Rive? Rive is an animation creation tool, and you can think about it in the spirit of the days of Flash, when it was used to create cool and awesome animations. And so you can create animations like the one you can see on the screen. But Rive lets you do a few other things as well. So for example, the engine that we have lets you create different animation states and mix them together on the fly. And to show you this, I'm going to flip over to this tab here. And what you can see here is this is one of the Rive animations, and it's running inside CodePen using our web runtime powered by WebAssembly. As you can see here, here's the animation. It's one animation state called idle, and it's running. And we can introduce other animation states by switching on the wipers. You can see here, it's a subtle effect, but these are 2 entirely different animation states playing and being mixed together. And it's pretty cool because I can go into the code here and I can see that I can flick through and I have my idle animation state and I have windshield. Oops. I have this one called windshield wipers. And I can go in and I can update this to another one, which I know is in here called bouncing. And then I will let this update. And then when I switch it on, we should get a much more dramatic effect where we can actually see these 2 things mixing much more nicely. So that's what Rive is about, is being able to create animations like this, which are interactive, they can be mixed, and importantly, can run across a wide variety of platforms. So this is the second half of what the software engineering team builds. We have to build this editor, which is built entirely or 99% in Flutter. which allows us to have web deployments, allows us to target Mac OS and others in the future as well. But what we wanted to do was build small, tight, performant runtimes across multiple different platforms. And at the moment, we have Android, we have iOS, we have Flutter, we have the web, and we have C++. And one of the big problems, or one of the big challenges we had was, how do you take 4 engineers and build all these things and manage to actually get anything out the door? And so what we came to was, we need a common low-level engine for all of our different runtimes. And so what we started with is we decided to experiment with C++ as the basis for this. And we built an animation engine in C++, and it runs at the core, which generates all those frames of animations and all the mixing that you saw earlier. And we knew that if we wanted to deploy to Android, we could use the NDK and it would probably be fine. And iOS is Objective-C++, which would allow us to mix and match these together. So these would likely work. But we were unsure exactly how we were going to approach the web because we didn't have that much experience with Wasm. And so the very, very first runtime we built was our web runtime in C++, using Wasm to create our underlying engine and then bridge it into the JavaScript world. So I want to caveat with, you probably all know more about Wasm than we do. We've taken a pragmatic approach to build it, to get it running. And we chose it primarily, A, because we knew we could compile C++, and we could use C++ as the core, but we also had done some research and we needed that like small size, performance, and we wanted web compliance. And Wasm seemed to give us all this. So that's why over the last 2 months, we took this approach to where we actually have our web runtime running today. To give you a very brief idea of, we're going to actually jump into code and Luigi will take you through how we've locked all this together. But our overall strategy was relatively straightforward. C++ generates those frames, it mixes the animations, it generates what you're seeing on screen, but it doesn't actually render it. So what we're using for that is, we could have created a renderer in JavaScript in whatever technologies, could have been WebGL, but what we decided to do was we decided to use Canvas with Context 2D and use that to actually render those frames coming from C++. So we have the engine, and we have our JS renderer, and the C++ engine is pumping those frames of animation up to our rendering layer at whatever frame rate is needed. And JavaScript in return is communicating back down to the C++ engine by saying, there has been this interaction, do this, or mix these 2 different frames of animations at these different time points together. And in fact, the JS rendering loop controls the frame rate at which it's rendering as well. So it's telling the C++ engine the time points at which it should be building the next frame. So we have this dual interplay, or this like loop, where C++ is passing data to the JavaScript renderer, and the JavaScript renderer is passing down data to tell the C++ engine what to generate next. There are 2 or 3 concepts here, which I'm not going to go into in detail, but when you look at code, it's interesting to see. You're going to see how we built our renderer in JavaScript, and you're going to see a couple of classes called RenderPath and RenderPaint. And these are sort of some of the boundary glue that we use to handle communication back and forth between these two layers. So when we started doing this, we quickly hit upon Inscriptum, and we said, okay, Inscriptum looks like it's an interesting route to go down. It's been around for a while. It can handle our C++ compiling. But when we looked into how we would build our Wasm, we ended up at a crossroads going, well, should we use Scriptums and Bind, or should we try out Web IDL? Both seemed viable options, and in fact, we have experimented with both and have 2 different implementations of our engine binding to JavaScript using both of these. But we started with Bind because we found that the documentation was broader. It was a quicker route. We could learn more quickly about how we could create these bindings. So we started with Bind, and that's what you saw running in the browser there. It's an NPM module that we serve up, and that is built using Inscriptum's Imbind. But then we experimented with WebIDL, and we did a quick comparison of the two, and we're still doing work at this. And we haven't quite decided exactly which route we're going to go, but we have both working, and we're going to talk briefly about the pros and the cons that we have found over 2 months of work. And this should be interesting, not only from a perspective of how we put it together, but what you're going to see here is folk who are coming to things like WebAssembly at this point in time and what their journey is like to actually starting to build with these things. Now, it kind of would have been nice to be able to play with Rust, because having looked at just Rust's ecosystem and the amount of information out there about creating Wasm from Rust. But Rust is great, but we have these natural bindings to Android and iOS. And so we stuck with C++ as something that would hold us in good stead across all of these platforms, including things like Unity and Unreal, when we get to those, because there's good application for our animation system there as well. So let's jump into the code side. And at this point, I will hand you over to Luigi, who will probably fire up his VS Code, and we'll start to walk you through some of the ways that we have built the bindings, how our compile chain looks like, and how we've tied it into our front-end renderer.
All right, give me a sec to see if I can figure out how to share my screen with this. I haven't used Zoom before for this. It says desktop 1, 2. Oh, I see it numbers them. Can you see anything? Allow. Sorry, give me a sec. What I wanted to show too was Zoom. Here we go. Oh, I have to restart. Sorry, I'll be right back. Of course.
Oh my goodness.
Hang on a second. Let me reshare my screen and chat briefly about if I can work out which one I was showing. That one. So while Luigi restarts, one of the things that we did was, and all of this is open source. We'll have links to our repos at the end, and you'll see that we have a Rive C++ repo, we have a Rive Wasm repo, and we also have Rive iOS and Rive Android. And it's interesting to see how we've taken this single C++ core and how we've got it to build across all the, oh, I see a dinosaur now. That's promising.
Sorry, I didn't mean to cut you off, Matt.
No, you're good. You're good.
So what I wanted to show real quick was just from all those concepts. I think I want to show you the code that Matt's talking about. But I also wanted to show you just really quick, just a couple brief concepts so that code makes a little more sense what these abstract things are. One thing is, I guess the very first thing is what a file is. A file is just something that you work on, and it's got artboards in it. And you'll see like this file has one artboard in it. It's got this dinosaur. It's got a few different animations. Actually, this one only has one animation, but the other one is like this soldier. And you'll see that this has a few different, it has 2 animations on it. And anyway, each file can have multiple artboards. Each artboard can have multiple animations. The code that we expose to Wasm gives you the ability to kind of load the file, see the list of animations. It also lets you query for things that are in here. So like I can go grab things like this is iGlow left, and I can manipulate it at runtime. I can move it. I can run custom code against it on top of what it's doing when it's animating. And so I guess then the first part that we're going to look at is kind of like from WebAssembly or from your platform layer or your app layer, what you need to be able to do is get a bunch of bytes, send those bytes into our C++ code that interprets them as this file and gives you back, exposes some kind of an API to iterate the artboards that are in there, the objects that are in those artboards, and then the various animations, apply them and render them. So just an example, this soldier that you see here in the editor, if I go over to our beta site, this is what's running. That's kind of our hero here. And you can see the fidelity is really high. It's identical to that animation you just saw in the editor itself. But this one's running all in WebAssembly, and it's mixed in with a bunch of other HTML5 layout and design and stuff. And here we do some other stuff, like we manipulate things. So this lets it follow my cursor. You can detect when you hover and trigger different animations. You can change the speed of the animations since they're all dynamic. Here again, you can mix different states in, all through the code that we expose to WebAssembly. So I guess if we start looking at what the code actually looks like, I think first and foremost, what a file looks like from the C++ side, the very basic thing that, the first thing that's bound into WebAssembly is the ability to kind of interpret those bytes. So that's our load operation, which is here. We do read. We have an abstraction for a binary reader, but basically the way we glue this, if we look at bindings, is we have a simple abstraction to load the file. We have a function that we expose, and then we just get the byte array. It took us a while to figure out how to pass, kind of from the last talk, to copying memory back and forth. It took us a bit to figure out how to do this, and it was even harder, I think, from the web IDL perspective, just because it wasn't as documented. But we did figure it out. Basically, just map a memory view. We instance a binary reader against it, get the file, and then we actually return the raw pointer back to Wasm. And the nice thing that we found that Embine does really well for us was basically do all the boxing and the unboxing of these raw pointers. There's nowhere in our JS code that we have to deal with pointers. We're always dealing with JS objects. So yeah, looking back at the notes that Matt had up there, those classes that we really care about is, once we've got a file, we have to have the ability to iterate the basically the artboards in that file. So first thing we expose is a load method. And then when we get the actual file itself, we have the ability to get let me see if I can find it, the artboards out of it. So this is all, if you've ever used Embine before, it should look pretty standard. We have some ways to get individual artboards by name, or you can get the default one, which the artist set up. And those are more references to classes that are exposed over to WebAssembly. And then each one of those, the artboard itself just has the ability to advance it, which means I can manipulate things, I can apply animations to it. Advance basically says this amount of time has passed. Update your internal state to match that and reflect that so that everything's ready to draw. And then you call draw. And this is where things get interesting. You call draw from the JS side on this artboard object that's exposed, passing in a concrete implementation of an abstract C++ class implemented in JS. And this is where we think the stuff that the Scripting crew has built is really phenomenal. The ability to define an abstract class in C++, implemented in JS, and have that interop work seamlessly is really, really nice. So basically our abstraction for the renderer that you pass into this draw call, from a C++ perspective, it's pretty similar. It's pretty simple. All it has is a few different methods exposed. It gets a little complicated when it needs more data that the system itself needs to generate. So for example, paths and descriptions of how those paths will draw on the screen, that's something that the internal system handles. And so those are further abstractions that basically the engine needs to build on demand, and you need to expose and build in JS world. But again, you get a pointer back from JS of the instance object, and you can use that with the right interface in C++ land. And then when you pass that back to a method that's concretely implemented in JS, Embine automatically gives you the JS reference to it. So that was really nice. It was also, it felt a little bit like cheating because we didn't really understand how that all really happened. WebIDL was a different story. We had to, we got a little more nitty gritty, and we kind of got to see how a lot of this stuff really works under the hood. What we realized there is that, so for example, if I jump over to the bindings for the IDL, if you're not familiar with this, basically it's sort of really similar to what we did in bindings for Embind, but it's just a kind of a pseudocodey way to mark up the code that's going to be exposed. So we have a bunch of enums that we expose, and then we have a bunch of interfaces that need to be concretely implemented. And basically we run some, I think it's a Python script that basically generates this glue code for us. And then we do kind of a master glue file that includes the generated one and kind of hooks everything up. And here you'll see that when we implement the abstract function to make our render paints and our render paths, which the engine calls when it loads in the file, we have to kind of call into JS, get back the boxed pointer, cast that to something that we know how to interpret in C++ land, and kind of marshal it that way. And similarly, when we call in from one of our abstractions, like let's see, something where we call like, let's see, draw from, when we call transform, for example, with a matrix, matrices are, they're basically all on the stack, and we have to sort of figure out how to get the pointer from it and cast that to a object that will exist in JS land. And so what you get here is actually this value that gets piped through is actually a pointer. And we kind of emulated some of the get cache methodology that Emscripten exposes internally to cast those back to pointers. So you'll see in like our implementation for this, which this is very much the WebIDL stuff is still really, really early. So we haven't really quite polished this up for publish, but you'll see that there's a lot of funkiness. Like we actually have to look up the pointers for a lot of this stuff. So let me see if I can find one. So when we get transform, we get a pointer object, and then we have to box that and find the actual JS object, call into Wasm to get with our reference with the JS object, such that then we can get back the real values that are bound in from our glue code. So it's a little funky. It's definitely the nice thing about Embind for us is that it really does abstract all this away. And hopefully one of you know how to make this cleaner with WebIDL. Maybe this is just the way it currently has to work. I know that it's still it's newer than a lot of the Embind code. But one of the really nice things that has kept us going with WebIDL is that the generated code is quite a bit smaller. In our case, it's almost 20% smaller. And our current runtime is pretty small. It's 110K. But as we start adding a lot more stuff to it, we know that that'll grow, especially as we start exposing more access to some of these low-level things. But the fundamental thing here that this solves for us, what Wasm does really nicely on the bindings that we get with both with WebIDL and with Embind really work well, is this fact of being able to have our C++ code be handed a binary blob, interpret that as something, generate a whole bunch of stuff that's abstract from the C++ perspective as concrete objects in JS, and similarly, there'll be concrete objects on Android and iOS and in Unity and Unreal. And then being able to marshal calls back to them. So being able to call the abstract methods on them and landing back into JS land. And there's a lot of things that we ran into with ES6 classes. We found a really nice way to make them work with WebIDL. We didn't find as nice a way with Embind. But there's definitely so much potential for both of these systems, and we really like how clean the final implementation ends up being, and that the abstraction layer between the two is very well defined, and so far has been really portable. We've been able to get it working on these 3 completely different platforms with a pretty simple abstraction between them all. And so if we can go back to the notes maybe, or I guess I could pull it up here. I kind of wanted to show real quick one of the things that we do to to get it down to such a small size. We optimize for size. We don't include assertions. We don't include runtime information and no exceptions. So this is kind of like, we use C++ 17 just because there's a few things from a few of the newer syntax things that are really nice and make it nice and clean, but we're kind of like, I don't know, an orthodox, I know that there's C+ is what people have called, but I think that's only approved to 11 or 14 or something. So we're not quite there, but it is really nice to be able to keep the runtime size so small. And part of the reason why we're able to do that is that we kind of have a preprocessor that generates a lot of our class information for us for a lot of the serialization and deserialization. And we can use a lot of the data that we inherently have from that to do kind of our custom RTTI, if you will. And that ends up taking way less space in the final binary. So yeah, I think I can hand it back to you, Matt.
Sure. Let me just wrap up and share back. There we go. And so yeah, we hit a bit of a crossroads, and we're still at it. We find both. We've got both Unbind and WebIDL working nicely for us. The Unbind code is smaller, and the Unbind code is frankly at the moment more legible and easier to maintain. But it generates currently 110 kilobytes. And as we expose, even just exposing another method or function call from our C++ to JavaScript makes that go up by a large number of bytes. So we're curious to see, as we start to grow the surface of the API, how that makes our WASM size explode. On the WebIDL side, as we said, there's sparser docs. The abstractions are less clear, or at least we're not grokking them quite as much yet, but there's a 20% size difference. So it's which way we go, we still kind of have to work out. But the nice thing is that our C++ core without modification is compiling down to WASM by either of these routes, and it is a lean, mean, and as far as we can tell so far, pretty performant engine running inside any modern web browser, which is really nice.
Yeah, that's one thing we really haven't done enough of is between WebIDL and Unbind. We suspect that probably going to be really similar, but we'd love to do a little more profiling around what really the impact is beyond the size, also for performance. There's a lot of lookups that happen that probably don't impact much, but we need to do more work there.
Nice thing is that all of the runtime code is open source. You can go to Rive-app on GitHub. You'll find our C++ core engine. You'll find our WASM code. You'll find our mobile runtimes for iOS and Android as well. The NPM package is up, and so the code that you saw on CodePen, of which there are 2 links down below, can be embedded there. I have it working in JS Fiddle. We use it across our websites, our beta website as well. It works really nicely. There is also a blog post if you're interested on the sort of the getting Rive to run inside your web browser. It's less about how it uses the runtime and more about how you use the runtime to be able to do what you want to do. And we're more than happy to make these slides available publicly if people want to grab those links and check things out. And with that, we just want to say thank you for your time. We are still fairly fledgling in our exploration of WASM. We're super happy with what we have so far, but we know that there are still a lot we need to learn. There's a lot that we can get from the community. And so we're always happy to get feedback on what we're up to. For those of you who are interested in digging in to see how we're using it to build an animation runtime. So thank you.
Yeah, thank you so much. We'd love to answer any questions, any complaints, anything egregious that you saw. We would really love to hear about it.
Are there any experts on scripting in the room? I see Alon lurking. I don't know if you had any feedback.
number 1 feature request from Scriptin. I think right now more documentation around the web IDL stuff. I think it's maybe it's just that it is what it is, and there isn't enough. I think we had to grok a lot of it from looking at examples and figuring out. Like one of the things that we ran into, for example, was that we couldn't. At first, it didn't seem like we could extend the classes that we were binding out, the low level abstract, the pure virtual abstractions that we wanted to implement in JS. We couldn't inherit from those with an ES6 class. And part of the reason for that was that some of the generated code was doing things like checking if the methods were defined directly on the object. We kind of just stabbed and hacked at the Python generator and removed that restriction. And then basically just defined them on the prototype, and that made it all of a sudden work with ES6 classes, which was really nice. And we feel like we're a bit stabbing in the dark with that. We don't know if that's if that was there for a reason, if there's a reason, if there's future work being done with that. Anyway, we would love to understand what where that's headed, and make sure that if we do decide to wholeheartedly embrace WebIDL, that we do it in a way that matches where the platform itself is going to.
Awesome. So we have a question on YouTube from Kenny. I'll read this one. What is the coding language for interactivity? JavaScript only or TypeScript externs?
Yeah. So as I was talking to who was it right before this in the breakout room? I'm starting to get the name, but the guy who talked earlier about the TypeScript, the assembly script stuff. Aaron, yeah, Aaron, that's right. And we'd love to figure out a way to build a scripting engine into the editor itself, such that people can write the code and edit with it and visualize in the editor what will happen at runtime. Right now, it depends on which platform you're hosting the code. So basically, our runtimes are effectively driven entirely from the code base that's hosting them. So in this case, on the web, it'll be JS or whatever you have available on the web that you can transpile down to. So you could write it in TypeScript, you could write the interfaces in really anything that runs on the web. But we don't have kind of a scripting language that you can input into the editor and then will be played back, if you will, at runtime on any of those disparate platforms. Although AssemblyScript looks really cool, and if we could figure out how to get something like a Wasm layer running on all those different platforms we talked about, we could enable a solution like that, a plugin architecture, an expression system, whatever. But yeah, right now on iOS, it's Swift and Objective-C. And on Android, I know we have Kotlin. I'm assuming it'll be fine to work it with Java too, but I know our examples in Kotlin. So the bindings that are exposed from our code base that I showed you, like the ability to get the different artboards, get an object and move it around, that's available on all those different platforms. And in JS, it looks, I could show some code if you're interested, but either way, it's basically you have an object and you query for its position, and you can set its position before you run the apply and the advance and the render stuff that I showed. I don't know if that fully answers your question.
Well, Kenny, if you follow up, feel free to drop in the chat. We have another question, I believe from Renee. Hi, I'm loving the Rive 2 beta. Any plans for a WebGL renderer? We'll be interested to see what code looks like when you take the path, etc., from Wasm and render them in JS.
Yeah, so right now we're just calling directly into context2D. So we chose the abstraction such that it would work fairly well across the platforms that we know have we took a look at what the renderers were that we wanted to work with, and we kind of chose our common denominator, something that kind of would work across all of them. So right now that's binding to context2D, but you could totally do that with WebGL. We have a lot of plans of doing something with it, from as simple as first just drawing the outlines of the shape and then kind of massaging in a more efficient tessellator that can also be that can also be threaded, potentially driving a lot of that from the C++ side and kind of passing off some the lower level instructions over directly to WebGL. The big thing that, because so much of this could be done on the GPU, we'd really like to kind of maybe consider just going for web GPU directly. But I think it's still something that's it's really experimental on our end, and it's something that we really want to do because it'll enable some of the higher performant scenarios that we want for things like game engines and the like. But it's still it's something we haven't quite tackled yet. It's really on the forefront of our minds though, and we can't wait to be able to get to it. It's we're really passionate about that. Cool. And if anyone's interested in helping us out with that, by the way, we'd love to talk to you.
Anybody in the Zoom has questions, feel free to drop it in the chat or just unmute yourself and fire it away. Ooh, one from Alon. For code size, do you try Clojure compiler?
We did, and the reason it's disabled up in the example that I had there was because of some of those ES6 things. We've got some code like some destructuring and some const and some ES6 classes, and we found that there were a few issues that we were having with running it through Clojure and the built-in minifier that Emscripten had. So we kind of did this really hacky thing, which I'd love to share my screen and show you just how hacky it is. Let me see, desktop 3. So what we do is we had to disable Clojure, and we, as our sort of post-amble, we inject a marker that then we awk out, and we run Trsor against it. And that was purely just to get our sort of the minifying working with ES6 and some of the more modern JavaScript features. And maybe we're missing something with why it wasn't working with Clojure. But I think it was when we had it without the ES6 stuff, it was definitely smaller with Clojure, but it wasn't far off using Trsor. And I think that the other thing that we realize is also the JS part of it compiles to almost nothing when we gzip it. So it didn't seem like it was worth spending more time there. It seemed where we were seeing a lot of the bloat go in was when we exposed more functionality. So for example, we have the ability to set the colors on things. As soon as we expose that immediately, the code's all there, but just those bindings that were exposed immediately started adding kilobytes. And so that's where we really got excited about WebIDL and finding some system that would keep that size a little lower. But we'd love to come back to Clojure and figure out either if we were doing something wrong with it or if there's more that we can do there.
All right, you have 2 questions from YouTube. I'll fire them off in order. From Simon, how is your experience writing editor in Flutter?
We loved it. We came to Flutter totally by kind of accident. We used to work with someone who's a big part of the Flutter team, and we reached out to them a few years ago, and they said they were working on this Flutter thing, and we kind of took a peek at it, and we really liked what we saw. And as an application building framework, it's phenomenal. The tooling that comes with it, the fact that it's kind of all works out of the box. You run a couple command lines and it's working. You don't have to kind of mishmash a bunch of different tool sets together. That's really nice. It comes with built-in a testing framework. That's really, really, really nice. The other thing that it has that we really like is kind of the performance tooling, the language itself. We really like Dart. We love that it's strongly typed. We love that there's really good implementations for the static analysis in VS Code. It's just all really a really nice ecosystem to work in. I think that time will tell what the future for our editor will be. If our bet on Flutter is gonna last forever, how long? But we've obviously looked at a lot of different options. The first iteration of Rive was built in in JavaScript. It was ES6, just Babel transpiling, some modern features, modern JS, and some WebAssembly. But mostly we were using a renderer in WebAssembly, but the rest of it was all JS code. But yeah, we really are huge fans of Flutter. We love the team. We love the feature set. And I think that if anyone else is considering it, it's, it's early days for them on the web, but we really, really like working with it. And we think we'll be sticking with it for a long time to come.
Cool. This may be the last question. We'll see. It's a follow-up from Kenny on YouTube. Thanks, Luigi. Does Rive have filter support like drop shadow and glow? And if so, what is the performance like with Wasm?
Not yet. The reason why is because we chose renderers that were kind of available to us on those different platforms at kind of natively. If we want to do drop shadows and glows, we really do need to get to something that gives us a lot more access to the low-level GPU. Doing that in something like Context2D would be, I mean, there are ways to do it. It wouldn't be really performant. We really want to do that with custom pixel shaders, the ability to draw to off-screen render targets and then blit those back on the same frame with more effects on them. There's so much more that we can do if we have access to a low-level system to do all those effects performantly. And we have ideas for how to do that, but again, that goes kind of back to the having a native or kind of our own renderer, a custom renderer for this, which is something that we definitely want to get to. But we also want to make sure that there will always be a nice, really super thin, small plugin that you can drop into any any website to run your animated icons and not have to host first of all, use up a WebGL context, but then also have to host a bunch of extra code around a renderer that you don't really need. So we're figuring out what that's going to mean, whether in the future there'll be a light version and kind of a more heavy full version, or maybe even kind of deliver that on demand depending on the contents of the file. We're thinking about all those things, and we definitely want those features in. Rive 1 has a lot of those features. We have masking, we have drop shadows, we have inner glows, outer glows, and all those things. And we were able to do that because we had a custom renderer, but we didn't have the ability to kind of provide a really streamlined, super lean experience. You got to bring in a 4 megabyte dependency anytime you wanted to host a 10 kilobyte file, and that made no sense. I mean, there are places for it, and it works really well where it does. I don't mean to say all the work we did before made no sense, but it is it definitely was a weakness, and we think that being able to answer the kind of lean, mean story first, and then kind of let people who really want all the features to buy into the bigger runtimes and adopt even more of our code base. That's great, but we want to make sure we have an answer for everyone else first.
All right, I think that is going to be the last question. And well, thank you, Matt and Luigi. Awesome talk. Yeah, we'd love to get that link to put in the description for YouTube later, and I'll get that from you after. But we thought we'd use the rest of the time to continue networking. If people are still interested in hanging around, we'll probably end the live stream because it's not going to be interesting for everyone else. But yeah, Betty, want to take us away?
Yeah, so I will go, I'll start the breakout rooms. And the other thing is, I noticed this last time, but if there's only like 1 or 2 people in a room, I'll just move you all to a different room because not everybody ended up joining. So give me 1 second.
All right, in the meantime, goodbye on YouTube.
Bye, thanks all.